Good morning. My name is Erdem Şahin. In this talk, the topic is Vergence-accommodation conflict. I believe most of you is familiar with. I will discuss different techniques to address different display technologies that could address solving this problem. So we will talk about the Vergence-accommodation conflict problem, and then after describing the problem, I will briefly discuss different display technologies, namely under two categories, which are basically enabling focus cues and accommodation-invariant displays. In particular, I will also talk about one of our recent works that we have been working on in the context of accommodation-invariant near-eye displays. So if you look at the existing XR display technology, especially commercial available displays, one of the biggest problems that has been hindering mass adoption of XR display technology is the viewing comfort. So viewing comfort is a crucial factor. When we talk about viewing comfort, we mean both physical comfort and the visual comfort. And when we speak about visual comfort, an important part of this problem related with the visual comfort comes from visual accommodation conflict. And this apparently is perceived also a big problem by the users of the current XR displays. So if we want to see the big categorization of 3D display, this is just one categorization, an example categorization here. We can roughly categorize the 3D displays in the stereoscopic, multi-view, and then on the right, accommodation-invariant and accommodation-enabling techniques. So from left to right, when we go from left to right, the main purpose is to create more natural viewing experience, create better visual depth cues or more depth cues more accurately. So basically, the main purpose is increased visual comfort. On the positive side, this is the goal, but then the trade-off becomes so that while achieving this, mostly we need to increase the hardware complexity or software complexity. Stereo displays, as we all know, provide stereo depth cues, and then in the context of VR, the motion parallax is delivered by simple head tracking. Multi-view displays add motion parallax on this without the need of wearing glasses. But the motion parallax is mostly discontinuous. This is one problem. When we speak about accommodation-invariant and accommodation-enabling, there is yet the main purpose is to add the correct focus cues, which are absent in these two categories. Or actually, in the case of accommodation-invariant, rather removing this dibular focus cue, which we will talk about it in more detail. So here, these two categories, as you see here, the main target of all these display technologies is reducing the Vergence accommodation conflict. So speaking about near-eye displays, it works that there is a display panel, and then we have a simple lens that projects image sharply on a single focal plane. When we want to show an image, at this depth, everything is fine. We can converge there due to stereo cues, and then we can also focus there because the focal depth is at that point. But once we try to show images at different depths, we can still converge there due to availability of correct disparity and Vergence cues, but we tend to still focus at or around the focal depth. So this creates the so-called Vergence accommodation conflict. And from vision science studies, we know that if this conflict is bigger than around 0.5 diopters, if this depth difference, this creates a serious problem in terms of visual comfort, causing nausea or eye strain. It's not the visual discomfort that it creates. It also reduces the visual performance. So people start fusing images or focusing images at longer times. It takes time to fuse and focus images. And furthermore, visual acuity is degraded. So you start seeing lower resolution images. So once we state the problem, the nature of the problem in existing stereo displays, the mismatch between this vergence and accommodation, now we can talk about the possible solutions. What kind of display technologies can address this solution, this problem? The first category is enabling focus cues. So the problem is about focus, right? So naturally, if you are able to enable focus cues, if you can deliver correct focus cues, as in natural life, then the problem will be solved. In this case, we can categorize the physiological depth cues of the human visual systems like in two main categories, like namely stereo cues and focus cues. Like the stereo cues are vergence and disparity. Focus cues are accommodation and defocus blur. Accommodation, like what our crystalline lens do, is driven by the defocus blur. So if there is a blur, defocus blur in the scene, we tend to accommodate based on this information. So there is this link here. And then convergence is driven by the disparity. So based on disparity, we converge. So these are the main signals, as you see here. And then there is also cross-link. So all these visual cues are, in a sense, work in harmony. In the case of this specific enabling focus cues, what we want to do is we want to maintain this link here. So we want to create correct defocus blur. If we are able to do this, then accommodation will be driven correctly. So what kind of display technologies we have here? On the left, there is varifocal and multifocal displays. So varifocal, so if you are able to use a varifocal lens, and if this lens makes this display focused at the depth that our eyes are expected to focus, then in a sense this will provide the correct focus cues. But still, it is, let's say, it approximates the accommodation, but the focus blur is still not perfect. So there is, again, a single focal depth. But in natural world, focal depth comes, in real world, like every object has focal depth at its corresponding location. So this is still an approximation. So defocus blur is still not correctly created in this case. But at least you are accommodating at the correct depth. The conflict is solved. In the case of multifocal, what is done is you simply create multiple focal depths by, for example, time multiplexing technique. You can use, again, a fast focus tunable lens, and then you can create these different focal planes. And they will always exist, basically. If you are able to use time multiplexing that is faster than your temporal resolution, eye's temporal resolution, so then you will be able to show images at these corresponding locations with correct focal depths. So the drawback here is like you need fast optics, basically, to cover all these depths. And then at the same time, you need to have a fast frame rate display. Like my colleague Frank talked about the light field display in the previous talk. On the right, you see one example, light field, and also holographic. Like the difference between left and right side is that the light field and holographic are the techniques that ultimately create the true light coming from a scene. Light field does it in terms of rays, geometric optics, and holography does it in terms of wave optics. So both these two techniques are, in a sense, the ultimate ways of creating 3D. But then, speaking about the possible drawbacks, we should mention in the case of light field resolution, if we especially use, like for example, microlens array-based light field displays, one typically needs to trade spatial resolution for the angle resolution. And then, in the case of previous talk, for example, it was a time multiplexing display. You can maintain high spatial resolution, but then you need to increase your, you need to have very fast display again, and then your full light field frame rate might be not that high. And in that case, you are limited with the temporal resolution. Holography is, of course, the ultimate way, but then there are still problems with the existing special light modulator technologies, especially in the bandwidth, the space bandwidth product is called, that is provided by these modulators. They kind of limit the eye box and field of view that you can get. So there is kind of trade-off between these two. If you want to get high field of view, good, totally immersive displays, you end up with very tiny eye box, which is not basically practical, or vice versa. You can increase the eye box, but then you will end up with not that immersive display. Speckle is another problem because of coherent imaging. This needs to be addressed for holographic displays. So accommodation enabling is like there is really quite a lot of techniques and quite a lot of research in there. In the second category, it is rather less pronounced, or let's say less popular in terms of the amount of study, or less known, let's say. So the purpose in accommodation invariance is this. I was mentioning about this crosslink here. So the main Q deriving the convergence is the disparity, and then accommodation is defocus blur, but then convergence is driven by the defocus blur Q as well. Or accommodation is driven by disparity as well. So the goal of this technique is that if we can eliminate the defocus blur Q, instead of giving it wrong, we can also remove it totally. In this case, we can rely on the correct disparity so that this disparity would derive accommodation correctly. So in that case, vergence and accommodation would be driven consistently. That is the idea. Some well-known techniques, especially the Maxwellian display is the most well-known technique in this domain. So the idea is basically projecting a 2D image in the eye within a small aperture of the eye. So if we can maintain this entrance pupil so that it is very narrow, actually smaller than our eye pupil, then the depth of field simply increases. And then by this way you can achieve extended depth of field and accommodation invariance. They are quite analogous to each other. If you achieve extended depth of field, this means defocus blur is removed. So everywhere this image is sharp. And then basically this is our aim. In that case, the displays become accommodation invariant. So the problem is here, as you can imagine, because this tiny entrance pupil is, if it is fixed, if you don't do anything, it is fixed. And in this case, if you move your eye a little bit, you basically lose the image. So the eye box is a big problem, like in holography. Another approach is time multiplex technique, using a focus tunable lens and then using, again, frame rates higher than human eye temporal resolution. Projecting images so that at the end of the day, you achieve point spread functions at different depths that are as focus invariant as possible. This was quite more recent work, and then in this case, one trade-off is, again, you need to use a fast optics, and you somehow lose some resolution compared to the case where you use directly 2D image as in normal stereo. So you cannot get as good as image as in traditional stereo. So another category, basically this is the same category, accommodation invariant, but a more recent work that we have been working, I will talk about this now, is called wavefront-coded accommodation-invariant near eye displays. So here what we try to do is recognizing the drawbacks of previous techniques. We still want to pursue the accommodation invariance, but we want to achieve this with a static optical element, like a diffractive optical element. Instead of using focus tunable optics, using a static diffractive optics, how we can achieve accommodation invariance. So this will bring us some advantages. So we would be, this is quite attractive to use such static elements in the VR displays because of several points, like for example, power consumption. So how the system works? Basically, this is a computational display. Right. This is a computational display. So it is nothing but a conventional stereo or conventional near-eye display, but with an addition of additional optics, like a diffractive optical elements. We insert these diffractive optical elements in the system, and we, at the same time, we incorporate an additional pre-processing algorithm, namely a neural network. So the combined effect of this pre-processing and optics is that we can achieve, regardless of the accommodation depth of the viewer, we achieve sharp images. And then this has been the idea, right? If we can achieve sharp images, we can achieve accommodation invariance. So basically, the problem in this case, how we solve the problem, we defined this, okay, let's have this diffractive optics, let's have this pre-processing. Then the question is how to find these elements. So in that case, we were using machine learning to basically find what DOE and neural network pair achieves this accommodation invariant effect in the best way. And then this is an example, for example, this is an example diffractive optical element that we learned. Here, this shows the phase profile of the optics. If you use this kind of optic with the corresponding pre-processing, instead of having this kind of point spread functions that you would get in a conventional stereo, which means you have a very sharp, it's not even visible, the point spread function here, very sharp image, let's say at this depth, very sharp PSF. But then when you focus back and forth, you see blur, like here. And then there's the reason you always want to focus here, right? But in this case, if you maintain the image quality similar, like here, based on this, then your accommodation will be driven or is expected to be driven by stereo cues. And one drawback still, we have been mentioning that, okay, this is nice, diffractive optics is static, etc. But then we need to mention one drawback, like there is a slight resolution loss still in the best focal state. Yes. So this is another example. This is actually the same display, but in this case, we show here the measurements in the lab. So what we did is we take some off-the-shelf, like existing display based on pancake optics, stereo display. Like we first measure these focal stack images with a, like let's say on this left side, with the lens itself. And then on the right side, we insert our diffractive optical elements and a pre-processing algorithm. And in this case, we measured the response for the wavefront coded AI case. Here also you can see the effect. Basically, you see the blur in the like lens only case, and then here you see the effect when you have this accommodation invariance. So finally, I can give the summary. So we talk about two main categories of techniques to address Vergence accommodation conflict: accommodation-enabling and accommodation-invariant. So in terms of XR display manufacturing, there are lots of trade-offs to consider which display to choose. It is still not very obvious which technique is the best because, for example, the complexity of optics, the complexity of software, the power consumption, the cost, all these things should be optimized by the given method. On the other hand, from the user perspective, it is still an open question whether this accommodation invariant display would be preferable or over accommodation enabling display. So there are studies showing that it really addresses the Vergence accommodation conflict problem. But then there are factors like losing some part of the resolution. So it should be somehow quantified what is better in terms of users. Right. Thank you.